Thank you very much. Our next speaker is Riccardo Notarpietro from EUMETSAT.
It looks like you're muted.
Yeah. Can you hear me?
We can hear you.
Okay, so can you see also the slides in
Yes.
presentation mode?
Yes.
Yeah, okay, perfect. So, good afternoon to everyone. So I'm Riccardo Notarpietro, and I apologize for me for not being there. Yeah, well, I am in Germany and actually it's also night. So I hope to be able to go to the end of the presentation. So what I'm going to show you is this comparative analysis of differential code bias estimation techniques for LEO GNSS receivers. So I wish to thank Doug from the UK, from UCAR, Jaden Lay from the University of Colorado Boulder, and Mark from NOAA for providing all the data, for also a lot of discussion with them. I wish also to thank my colleagues in EUMETSAT in the radio computation team, Axel, Chris, and Saverio, Sebastian, and Veronica for their help in doing this kind of analysis. So you know very well that the differential code bias is an hardware delay introduced by the transmitters and the receiver, and it strongly impacts the estimation of the absolute total electron content. The transmitted DCB from one end is estimated from ground-based measurements. Is made available normally from through the IGS from different processing centers, so you can have this. But the problem is that the receiver DCB should be estimated as part of the total electron content computation. And unfortunately, this is strongly sensitive, as I'm going to show you, to the data selection, to the algorithm we are selecting. And so this is mainly the rationale of my talk. So if, let me go to the outline of my talk. So I'm going to present two different techniques for estimating the DCB of the LEO receiver with the pros and cons for each of them. I'm touching what I've used as data set and the processing strategies that we have applied. And then I'm going to show you a comparative analysis of the LEO DCB produced by different centers. Then I will move to my conclusion. So the first technique is the so-called zero-tech technique. So this assumption for this technique is that the TC at high latitude during night and high elevation is negligible. So this means, looking at this equation, that the minimum of the absolute slant tech should be zero. No? This means that looking at this equation, okay, this provides us a direct, let me say, way to compute the receiver DCB, which is minus the minimum of the relative slant tech of this term, which is basically the measured slant tech already compensated for the transmitter DCB. So the only cons of this approach is that observation should be taken where the spheric effects are weak. And by formulation, if you look at the formulation, the zero tech can overestimate a little bit the LEO DCB. So Zong, who proposed this kind of formulation, demonstrated that this overestimation is around 1 tech unit, but it was in low solar activity conditions, so it can be more in case of high solar activity. One other thing that I want to show you for this technique is that as a second assumption, in order to have a significant amount of measurements taken where the ionosphere is weak, we need to consider that the DCB of the receiver is constant over a given interval of time, maybe a few days. So in this case, we can compute the distribution of the minimum relative slant tech. Here is an example for 1 day of observation from a spiral satellite. And we need to consider a certain, let me say, percentile of this distribution to be representative of the LEO DCB. Normally it's taken the 25th percentile of the distribution. Then moving to the other techniques, the least square solution. This was first introduced by Yu et al. Here is the paper. And I believe that this is the baseline for the UCAR processing of cosmic and cosmic 2 data. So in this case, for any epoch and for any given pair of contemporaneous satellites, the vertical tech is supposed to be the same. So this is a strong assumption, which is underlie another assumption that the ionosphere should be spherically, at least locally spherically distributed. But in any case, in order to have the same vertical take from two different elevation angles, this means that the absolute slant take, which is this term, verticalized by a mapping function should be the same. And this provides us a way to compute an instantaneous receiver DCB. Here is the equation. So at the end of the story, the LEO DCB can then estimated by the least square solution of a system of equation like this. This equation is valid for each pair available and for each epoch. Looking at this equation, we have to assume something also on this term, which is the mapping function. And normally, the Kierkegaard's mapping function is used for this kind of applications. Here is the formulation. Here you can recognize this R-ion term, which is the distance from the Earth center of the thin layer where we're supposed to collapse the ionosphere. And from the surface, this is called ionospheric effective height. Here is the formulation for this ionospheric effective height proposed by Zong, which is, let me say, is function of the height of the LEO and of the solar flux here. So for a satellite which is flying at 500 kilometers, in this period, which is a high solar activity period, this value is almost 1,300 kilometers. But in the least square solution, you can use other different ionospheric effective heights. And as far as I know, UCAR is using 4,000 kilometers for this kind of parameter. This technique, the least square solution technique, has a lot of more stronger cons. So first is based on this ionospheric spherical symmetry distribution assumption. So exceptional care must be taken in selecting good pair of observations. In particular, the observation should be close between them, but not too close, because if not, let me say the receiver DCB starts to be not determined. In order to avoid this problem, we need to bound somehow the value of the difference of the mapping functions here in the denominator to a certain threshold. And depending on the threshold, again, the results are quite different. Another very, very bad cons of this technique is that, unfortunately, it strongly depends on the selection of the ionospheric effective height. Here is an example of the EUMETSAT processing. So in red is a daily, let me say, a daily DCB time series, okay, estimated with the least square solution approach, when the ionospheric effective height is supposed to be 1,300 kilometers. Here is superimposed also the zero-tech solution. You can see this is more stable, but in any case, the least square solution is going around. This is reported also with 95% confidence level. The dynamic of the least square solution is around 6 tech units in this case, for this particular satellite, which is FM 126. Here below is the same, but the least square solution is computed considering an ionospheric effective height of 4,000 kilometers. So you can see that things starts to get crazy. The dynamic of the least square solution is bigger, 10 tech unit, and the solution differs quite strongly. But the zero tech does not change because it does not depend on the ionospheric effective height. So for the analysis, we have taken level 0 NavOps data from Spire in the framework of the NOAA Commercial Space Weather Data Pilot Project introduced by Mark before. We consider 18 satellites over 60 days. So we apply the standard preprocessing technique, we detect cycle sleep, we split arcs, and then we consider only arcs taken at latitudes greater than 50 degrees in order to have some kind of ionosphere that is weak or something like that. And the arcs should be longer, at least 240 seconds. Then we took the DCBs for the transmitter from code. We applied the standard carrier phase to pseudo-range slant tech leveling. This was following the approach of Nick Pedatella. Without applying any local multipath correction, because at the end we selected observation taken with elevation angles bigger than 45 degrees. So for us, this is not a problem. For the zero-tech technique, we need to take data where the ionosphere is weak, so we consider only data taken by when the LEO satellite and the IPPs, the ionospheric pierce pointed for any given satellite, is in the Umbra region. While for the least square solution, the angular separation between each pair should be less than 40 degrees and the mapping function difference greater than 0.1 as the threshold. For what concerns all the other centers, so UCAR provided, UCAR and University of Colorado Boulder provided DCBs for the same receivers during the same time period using the least square solution approach. UCAR with ionospheric effective height of 4,000 kilometers, while University of Colorado Boulder with the two possible values. Unfortunately, for the case of 1,300 kilometers, they provided data only for the first 14 days. We at EUMETSAT, we process the data also with the zero-tech approach. Here is to complete this, let me say, the time series of daily DCB receivers for the satellites 126. Here, okay, in the red is the least square solution for that we have obtained with ionospheric effective height of 1,300 kilometers, with a mapping function difference greater than 0.1. If we selected other pairs with mapping function differences, which are a little bit bigger, okay, you can see that the other solution are here reported. Everything is going to be crazy. We show here also the zero-tech solution in blue, here, which is more stable, and also in green, the University of Colorado Boulder solution with the same ionospheric effective height and the same kind of algorithm. So the agreement is quite good. Here is the UCAR solution. So this, but the point is that the difference, is a big difference, up to 10 to 15 tech units, is, in my view, only due to the selection of, to the use of a different ionospheric effective height, which is 4,000 kilometers. Here is the case, are other examples for other three satellites, worse and better, when the least square solution computed for an ionospheric effective height of 1,300 kilometers is compared. So yeah, so this is the red is EUMETSAT solution, the University of Colorado Boulder solution in green, and the zero-tech solution is here. So for different satellites, the agreement is quite good. Here is the case when we are computing the least square solution with ionospheric effective height of 4,000 kilometers. So all the solution, EUMETSAT in red, green, University of Colorado Boulder, are going towards the UCAR solution. In particular, for these satellites, the agreement is really, really good. But what I want to stress again is that the zero-tech technique is independent from ionospheric effective height. And the better agreement is when the ionospheric effective height is selected to be 1,300 kilometers. Here, just to finalize, is let me say, is a summary of this inter-center comparison, and we have taken all the possible combination between DCBs estimated with two different approaches. We computed the difference and averaged the difference of the daily DCB over the entire period, and plot this satellite by satellite. So in case we are using least square solution for ionospheric effective height of 1,300 kilometers of zero-tech, the agreement between all the solutions that we get and all the center is below, let me say, 6 tech unit, except for some strange satellites that, okay, things are getting crazy. The same kind of agreement is achieved when the least square solution is computed for ionospheric effective height of 4,000 kilometers. Again, we are at the level of 5 tech unit, more or less, except for some particular cases. Things are completely crazy when we compare DCBs computed with least square solution, but with different ionospheric effective height. Okay, so I can move to my conclusion. So the scope here of this talk was not to validate LEO DCBs estimates from different centers, but to raise this kind of warning. So on the sensitivity of the data to the data selection, to the algorithm used to compute the LEO DCB, and to parameters used in the least square solution, like the ionospheric effective height. We have to really to be careful in using the correct one before comparing DCBs. And then my takeaway of this is that the best option when we want to assimilate absolute slant tech measurements in data simulation system is to assimilate maybe those derived by carrier phase, which are free of DCB. So these are more precise, I would say. So this is what I wanted to say. Thank you for your attention. Sorry again to be here. And if you have some question, I'm ready to answer.
Thank you. Do we have a question?
Hello, Riccardo. This is Doug from.
Hi, ciao, Doug.
Thank you for your interesting talk. Couple quick notes. I think you took DCBs from us when we were partway through our development. It's quite possible that our Spire DCBs are better these days. That's one thing. The other thing is that there is a least squares approach due to Stig-Syndergaard that does not require a minimum separation constraint. So
Okay.
I found that to be a more stable way of doing things.
Yeah, but then let me say the spherical symmetry assumption is gone. If you take data from, let's say, separated of 90 degrees, maybe in any latitudes, the spherical assumption is gone, probably.
I think you still have to constrain them on a certain maximum separation, but I think the minimum separation requirement is not.
Okay, sorry, yeah, I understood, took the point, yeah.
So just a couple thoughts.
Thank you very much, Doug.
Hi, Riccardo. This is it on?
Hi, ciao.
Yeah. Thanks for the nice talk. Just a quick question. I can tell from your slides, is the different? It looked like even when everyone used the same, effective height, you got quite a bit of dispersion among the results.
Yeah.
How does that difference compare to using a different effective height? I couldn't tell.
But yeah,
where does the dominant error come from? The effective height or some other?
No, I believe it's effective height, because in this plot, wait, slide before, maybe it's bigger. So here we are comparing solutions with different effective heights. Okay, so you can see that let me say, we can have error up to 14 tech unit easily. But you can have also for some satellites good let me say agreements. So, but I would say that the selection of the ionospheric effective height, if you want to compare different solutions with different effective heights, that starts to be really, really crazy.
Okay, thanks.
Yeah.
Thank you. Thank you very much.
Yeah.
One more talk? No, okay. Oh, okay. So I think that brings us to the end of this session. So thank you all so much, and let's thank our speakers again.
All right, just one announcement. So we'll go into the poster session. I think we had a cancellation, so we're done a little early. Hopefully they'll excuse that. But keep in mind, one thing that's important for the poster session, I think everybody from last time knew they were upstairs. Keep in mind, if you're on that side,